Thank you, Eric, for your kind introduction. I will present the results of my colleague from the University of Dresden and of our university, the Technical University of Freiberg. Why did we perform such investigations? We all know that the components are subjected to cyclic loadings during their service life. As an example, I show you some wind turbines and some airplanes, and in both cases we have high-reinforced plastic component sites, as you can see here. And we've got a big problem. For metallic materials, we can weld these parts together, but in this case, we could not weld the parts. So we had to use other joining processes, for instance, bolt rivet joints. And the problem of it is that we damaged the material. It means we threw a hole inside it, and due to the hole, we destroy the fabric layer, and furthermore, we put screws on it, and so we get some compressive force in this direction. These compressive forces leads to interlaminar fatigue crack growth. Another example are the turbines, the fat plates, and as you can see here, they were clamped like this, and we also got some interlaminar fatigue crack growth inside. Let me just shortly introduce you the material. On the one hand, we had a matrix, and on the other hand, we have a fabric. And in our investigation, we investigated 3 different fabric weights: a fabric weight of 160, 200, and 245 grams per square meter. And this together gives us our carbon fibroplastic composite, which is an orthotropic material, as you can see here. How to simulate these bolt rivet joints? We made a specimen with a whole notch arrangement, and we performed uniaxial as well as biaxial tests. In the middle of the specimen, we got the crack path, but unfortunately, or well, not unfortunately, the course of the crack path is predetermined due to the fabric layer. To get a feeling about the fatigue crack growth for uniaxial loading, so for interlaminar or fatigue crack growth, we performed uniaxial tests as well as biaxial tests to test the influence of the compressive forces. But this leads to a problem. Of course, if we have compressive forces in this direction, we have a more or less closed crack, and due to the closed crack, it's difficult to determine the crack tip position. We performed our test on 2 different test systems. The uniaxial test performed on an MTS 810, and the biaxial tests were performed on an Instron 8800. On both systems, we applied a camera system, and our specimens were clamped and put a speckle pattern on it. Our experimental procedure was nearly the same. We investigated 2 different tension forces, and we investigated uniaxial loading and compressive loading in biaxial case with 0.5 and 1.0 kilonewton. The test procedure itself, the important thing is that we performed 2 load cycles with 0.5 hertz, and we recorded the image sequence meanwhile. And so we got the full field for 2 load cycles. Afterwards, we performed 23 to 10,000 load cycles with 5 hertz just to get a fatigue crack growth. And afterwards, we repeat step 3 and 4. At the front, we have a blue Cooper camera with a resolution of 11 microns per pixel. And afterwards, we perform digital image correlation with GOM RMS. The digital image correlation was used for different things. In the first step, we determined the maximum shear stress in this area. And afterwards, we determined the position of the crack tip of the closed crack using crack pi. I think David will explain the crack pi later. And as we know the crack tip position, we applied a virtual measuring clip and determined the displacement fields. And with this displacement field, we determined the energy release rate. I will explain later how it works. To get an analytical idea of the energy release rate, my colleague performed finite element calculations, but you all, it's not me, you all know that they are just as good as the assumptions. He assumed the 2D plane strain model in Abacus as an half model with orthotropic material and used a linear elastic material model. And so he also assumed that we have symmetric crack growth. And so we could calculate the energy release rate. But you all know we knew the material parameters, the loading, and the results are only as good as the assumptions we made. If we miss some information or had incorrect assumptions, we had a problem of the energy release rate. And so we tried to use our invented virtual measuring clip, which determines the stress intensity factors and energy release rate by measuring the displacements in the area of the crack tip. We used it before in an austenitic stainless steel, and so we saw or we clarified that crack branching and the kinking of the crack pulse. So the idea was it also to use for this material. And we just did the Young's modulus, the transverse contraction at the stress state, the displacements we got from the DIC. And so the results were measured values. The idea of the measuring clip goes back to Schwalbe et al., who measured the crack opening displacement, and we modified it. This means we applicated it directly at the crack tip and adjusted this continuously as the crack goes on. Furthermore, it's important to align it perpendicular to the crack growth direction. I will show you on the next slides some examples with the CT specimen. It's just to understand, because of course we applied it at our specimen, but I think in this way it's easier to understand. First of all, we applied our clip between minimum and maximum load. For an easy understanding, we applied it at mean load. This means the displacement field is 0, as you can see here. If we unload, you can imagine crack closes. This means the upper crack edge goes down, the lower crack edge goes up, and you see negative and positive displacement in crack growth direction and in perpendicular to crack growth direction, and the movement in this direction in the crack growth direction, as you can see here. And if we higher the load, we have also a symmetric displacement field, which is vice versa to this. So if we have crack growth, the clip goes on, and if the forces are equal, you see the displacements became larger. Which advantage did we have? As you can see here, the displacements due to the symmetry of the clip cancels each other out. This means we have the distance of the measuring points and the displacement of these 2 points. And we did not measure the displacement in crack growth direction for mode 1 loading. If we now take a look at mode 2 loading, the displacement fields are also symmetrical, and you see they differ. But if we take a look at the measured displacements in crack perpendicular to crack growth direction, the displacements for mode 2 loading cancel each out. It means we just get the distance of the clip. And on the other hand, we measure the doubled displacement in crack growth direction. So which advantage did we have? If we now have a look at a mixed loading load case, now you see the displacement field is not symmetric anymore. But now if we have a look at the displacements, you see we measure the pure mode 1 and the pure mode 2 displacement, and this means we can calculate the mode 1 and mode 2 stress intensity factors for its own. How does it work at our specimen? Here you can see the specimen at different load cycles, and now we have just one load cycle, and we measure the displacements at these 2 points, and afterwards we had different ways to calculate the stress intensity factors and equivalent stress intensity factor. On the one hand, we calculated the mode 1 and mode 2 stress intensity factor, which was easy because we just needed the range. This was a discussion we had at the presentation before. And afterwards, we could calculate the mode 1, mode 2 stress intensity factor, as well as the mode 1 and 2 energy release rates using Collisor's formulas. But if we want to have a look at the equivalent stress intensity factor and equivalent energy release rate, it becomes kind of more complicated. Due to the application between minimum and maximum loading, we have to normalize our displacements first of all. Afterwards, we calculated the time-dependent values for K1, K2, G1, and G2. And with the time-dependent values, we calculate the equivalent time-dependent energy release rate and stress intensity factor. Afterwards, we calculated the extreme values, and at the end, we got the equivalent energy release rate and equivalent stress intensity factor. How does it look at an example? We had a specimen with 25,000 load cycles. The reactive was here, and we had a compressive load of 0.5 kilonewton. This was the displacement, the complete displacement, but now we divided in mode 1 and mode 2 displacement. And as you can see here, we have the 2 load cycles I explained before, and you see the mode 1 and mode 2 displacement. And now if we have a look at the energy release rate, here the orange line is a literature value for mode 1 loading. And so we had the mode 1 and mode 2 energy release rate and an equivalent energy release rate, which corresponds to the literature. Now I'd like to compare the results with the finite element resolution and also with different weights of our material. As you can see, the mode 1 portion is very low, so we had a strong scattering, and the mode 2 is more or less in one area, but you can see with a higher weight, the fatigue tracking growth is lower. Now, if we have compare the equivalent energy release rate with the finite element, here's the finite element calculation, and here's our determined values with the virtual clip. You see that these values correspond to the literature, but the problem is that we assumed a symmetric crack cost, so that we are not sure if these values are correct right now. And now I'd like to show you the comparison of uniaxial and biaxial loading. The scattering of mode 1 is, of course, much higher because the crack is closed. For mode 2 loading, you see it's more or less one area, and you can see the compressive loading that leads to a slower fatigue crack growth. And here, these points are 1 kilonewton. This means the higher the compressive loading is, the slower the fatigue crack growth is. And furthermore, you can see the higher the brick weight is, the slower the fatigue crack growth is. At the end, I'd like to summarize. I showed you the virtual measuring clip, and you saw it was a low measuring expeditor, and it was possible that we measure the pure mode 1 and mode 2 loading due to symmetry. We don't need an origin to measure the stress intensity factors, and we had a variable gauge length. This means independence of the specimen size we could vary. We got a high amount of available data, and it's also an optical measurement process. This means we did not destruct our specimen. Of course, we have some disadvantages. If we have an inaccurate position of the grab tip, we got wrong results. And if we have a uniaxial loading, it could be possible that only one crack flag moves, and due to it, we got wrong results. What is necessary? The knowledge of the crack tip position and the displacement field for 1 or more load cycles. And I showed you that the description of the crack growth was possible. The increasing of the compressive load resulted in lower energy release rate, and the higher the fabric weight was, the lower the fatigue crack growth rate was. And in the future, we have to perform finite element calculations for asymmetric crack paths and also for the biaxial loading. And at the end, I'd like to say thank you, Eric and his team, to support me at CrackCoin, and also the German Research Foundation to fund me. And now I'm happy to answer your questions.